alkenes are unsaturated. And that one little difference, it makes them super reactive and the perfect building blocks for all sorts of things, from plastics to alcohols. Let's see how they do it.
So, what does unsaturated really mean? Think of it like a bus that still has some empty seats. The molecule doesn't have the maximum number of hydrogen atoms it could possibly hold. And why is that? It's because it's got at least one carbon-to-carbon double bond. This double bond is the heart of every alkene. It's what we call the functional group, and it's the source of all its interesting reactive chemistry.
So here's our game plan. First, we'll cover the basics of what alkenes are. Then we'll see how they're made through a pretty intense process called cracking. We'll look at a simple and actually kind of colorful test to identify them, and then we're going to jump into their signature reactions, the key to why they're so versatile. And finally, we'll wrap it all up with a summary and some really important exam tips to make sure this all sticks. Right, Section 1. Let's get to the core of what makes an alkene an alkene. It all boils down to one single feature, that carbon-carbon double bond. Alkenes are part of what we call a homologous series. Now that just sounds fancy. Think of it as a family of compounds that all look and act pretty similarly because they share the same key feature. And in this case, that's the C double bond C, the functional group. This whole family can be described by one simple general formula, CnH2n. For every carbon atom, you have exactly double the number of hydrogen atoms. Nice and easy to remember.
Let's meet the first few members of this family. We'll start with ethene, C2H4, the simplest one with just 2 carbons. Next up is propene, C3H6 with 3. You see the pattern here? The first part of the name, F for 2, prop for 3, tells you how many carbons there are, and that ene at the end is our signal that there's a double bond hiding in there. As we go on to but1-ene and pent1-ene, the chain just gets longer, but that simple CnH2n formula, it always works.
Okay, so where do we get these incredibly useful molecules? Well, you don't really find them just lying around in nature. We actually have to make them, and that brings us to their industrial origin story, a process known as cracking. Cracking is, believe it or not, exactly what it sounds like. See, crude oil has tons of these really large, long-chain alkanes, which honestly aren't in very high demand. So what do? We literally crack them under intense conditions. We break them down into smaller, way more valuable molecules, things like the fuels we need, and, of course, the super reactive alkanes that are the starting point for the entire plastics industry. Now, this process requires some serious industrial muscle. To break those strong carbon-carbon single bonds in an alkane, you need some extreme heat. We're talking 600 to 700 degrees Celsius. And to make it all happen efficiently, a catalyst like alumina or silica is thrown in to speed the whole thing up. And here's what you might get. You take a big decaying molecule, pass it over that hot catalyst, and snap, it breaks apart. In this case, it breaks into 2 really useful products, a smaller alkane, octane, which is a key part of gasoline, and the incredibly valuable alkene ethene, which is the starting material for all sorts of plastics and alcohols. So how can we actually prove that an unknown hydrocarbon has that all-important CC double bond? For that, we turn to a simple, classic, and visually pretty cool chemical test. So, how do we show this difference in the lab? Well, we take advantage of their reactivity. Saturated alkanes with only single bonds are pretty boring. They're quite unreactive. But that double bond in an alkene, it is ready for action. And this difference becomes crystal clear when we add a chemical called bromine water. The test itself couldn't be simpler. You just add a few drops of this orange-brown bromine water to your sample and give it a good shake. Now, if you have a saturated alkane, it just ignores the bromine. Absolutely nothing happens. But if there's an alkene in there, its reactive double bond immediately goes on the attack, kicking off a reaction. And the key observation, the thing you're looking for, is this dramatic and instant color change. A positive test for an alkene is seeing that bromine get all used up in the reaction. As it reacts, its orange-brown color just vanishes, leaving you with a colorless solution. It's the definitive chemical thumbs up for unsaturation. This amazing reactivity leads us right to the main event for alkenes, their signature chemical move, the addition reaction. This is what that double bond was born to do. So, in an addition reaction, one of the 2 bonds in that C double bond C, it's the weaker one, it just breaks open. This frees up those 2 carbon atoms to each form a new single bond with something else. The key takeaway is super simple. Two reactant molecules combine to make just one single, larger product. That's it.
First on our list is hydrogenation, where we add a hydrogen across that double bond. Now, this isn't easy to do. It needs a nickel catalyst and a temperature around 150 degrees Celsius. But under those conditions, you can turn an unsaturated alkane like ethene right back into a saturated alkane, in this case, ethene. This exact kind of reaction, by the way, is used to turn liquid vegetable oils into solid margarine.
Next up, we have hydration, which is just adding water, usually as steam. And this is a hugely important industrial process. The conditions here are even more intense. 300 degrees Celsius and 60 times normal atmospheric pressure, all happening with a phosphoric acid catalyst. This is how we mass-produce ethanol, the alcohol that's used in drinks, as a fuel, and as a powerful industrial solvent.
Now for halogenation, which is the exact same reaction we saw with that bromine test. A halogen, like chlorine or bromine, can add itself across the double bond. And what's really amazing here is the contrast with the last two reactions. There's no high heat, no pressure, no catalyst needed at all. This reaction just happens, easily, right at room temperature, which really shows you just how reactive that double bond is.
And it's a similar story when we add a hydrogen halide, like hydrogen chloride gas. Once again, that double bond readily just opens up to add the atoms across it. And just like with the halogens, this happens at room temperature. The ease of these last two reactions is a perfect illustration of all the chemical potential that's just locked up inside an alkene's double bond. Okay, we have covered a ton of ground. Let's bring it all back together and really focus on the absolute must-know essentials, especially if you've got an exam coming up.
This summary table right here, this is your key to success. It lays out the 4 main addition reactions we just talked about. Now pay really close attention to those conditions. See how hydrogenation and hydration need tough conditions, heat, pressure, all that stuff, while the reactions with halogens and hydrogen halides just happen at room temperature? Memorizing these details is absolutely critical.
And here are some final pro tips to make sure you get every possible point. Be precise. Always draw that C=C double bond clearly. It is the star of the show. When you're describing the bromine test, use the exact words orange, brown to colorless. Know those specific tough conditions for making ethanol die hard. And never, ever forget the golden rule. In these addition reactions, you always end up with just one single product. Get those details right, and you'll be golden.